Thank you very much. Thanks to the organizers for giving me the opportunity to present what I have been doing in the last few years, together with Luigi Castiglioni, who is a postdoc in Milano Bicocca, Marcia Tense, who was postdoc, and now she is in Brazil, Nadav, Diego Trancanelli in Modena, and more recently with Marco Bianchi, based in Santiago, Chile. What happened here? Okay, so let me start with a few motivations. Probably I could skip this slide because if you are here today, it's because you know and you are interested in the fact that defects, boundaries, interfaces play a big role in nature, let's say. So we have a lot of physical systems that have defects or impurities or interfaces, blah, blah, blah. But I would be now more formal, and I will try to motivate my talk thinking from our point of view, sort of string theory community, which are the main reasons why we are interested and which kind of investigation we will do about defects. So more formally, I would say that boundary and defects appear in string theory. Think, for instance, to d-branes. The boundary of the ADS spacetime is crucial for formulating the ADS-CFT correspondence. Defect and boundaries may support symmetries, and this is one point that will drive my talk. It may be supersymmetry, so we can talk about supersymmetry preserving defects. It may be topological invariance, so we can talk about topological defects, and so on and so forth. Or conformal invariance, and then we have conformal or superconformal defects. This is another reason, the fact that the study of the theory, of course, if the defect is dynamical, it will interact with the bulk degrees of freedom. Therefore, studying the defect is, the study of defects is strongly correlated with the study of the bulk theory. And we can learn mutual information between bulk and defects. And last but not least, this is also something that I'm very interested in. You will realize that kind of defects I'm going to talk about are Wilson loops, and Wilson loops arise naturally in the framework of higher form symmetries, because we know that higher form symmetries have generators that can be described by generalization, let's say, of Wilson loops, which are Wilson surfaces, Wilson. What happened? Because this is I should increase the time of life of my computer. Okay, but I'm not going to use slides for a long time. Most of the talks will be at the Blackboard. This is just for motivations. So I was mentioning that, in fact, Wilson loops or generalizations of Wilson loops like Wilson surfaces or Wilson's hypersurfaces are associated with the generators of higher form symmetries, and in turn they are charged under higher form symmetries. So this is why we are very interested in studying this kind of defects. Which kind of defects I have in mind? I will focus on defects in gauge theories, and for this kind of defects we have a sort of classification. We can talk about order type defects, and these are described by the insertion in the path integral, in the functional integral of non-local operators. And the typical example is the Wilson lines, Wilson loops. So what we define is a path integral where we insert the Wilson operator that is sort of the exponential of the holonomy of this connection L. And this insertion is interpreted as modifying, because W carries degrees of freedom, dynamical degrees of freedom. This is interpreted as modifying the vacuum of the theory. So we are dressing the vacuum with W. Then we have disorder types defects. These are typically Toft lines or Toft loops, and they arise when we have ordinary functional integral, but with non-trivial boundary conditions, typically singular boundary conditions. That can even have the kinematical defects. These are defects that do not carry any dynamical degrees of freedom, but they are basically submanifold supporting spatial sectors of bulk operators that typically are protected. And one example is the topological line, for instance, in 3 dimensions, and the chiral surface in 4 dimensions. Today, we are interested in studying Wilson loops. So we will consider this category of non-local operators. Let me just remind you that if I talk about Wilson loops in gauge theories, the first thing that you should have in mind is an operator that in the more general non-abelian gauge theory is written in this way, where the integral is over a given circle, and the circle, sorry, a given path, given contour. The contour can be closed or open. We will focus only on Wilson loops defined on circles. Fine. This is the typical, the usual definition of Wilson loop. What can we do with it? Why do we identify this Wilson loop with defect theories? Yes. Sorry, which ones? Yes, well, at least what we have, what has been introduced so far, yes, they are typically topological sectors. Yes. This is, could be, this is, think of perturbation theory. Instead of having the ordinary vacuum, perturbative vacuum, this is dressed with W. It means that, but it will be more clear later when I introduce also correlation functions. Okay, so why can we associate such an operator, roughly speaking, because this is not actually what I'm going to consider in general, to a defect theory, because of course this contour C defines a one-dimensional line inside your bulk space-time, and what we can do is to observe that, for instance, if you introduce Wilson loops in conformal field theories, it may happen that the Wilson loop preserves the one-dimensional conformal algebra, which is this one, SU11. So it is, basically on this contour, you may define a one-dimensional conformal field theory, which will be featured by which observables? First of all, the first observable that we have to introduce is the free energy, so the log of the partition function where you have introduced this non-local operator. And moreover, as you know, typically for any conformal field theory, the typical set of observables are correlation functions. How do we define correlation functions in this case? Correlation functions are defined for operators. Now, these O are local operators, localized on the contour. And the definition of this partition function, the end partition function, is nothing but the vacuum expectation value on the usual vacuum of the trace of this string of operators, where you have to insert W in any intermediate place in order to suitably covariantize the expression respect to gauge transformations. So this is the definition. So for instance, if you are working with a C, which is a circle, basically what you can do is to compute this correlation function, and you can compute it using different techniques. If you are working at low, for small coupling constants, you can use perturbation theory. If you are working at strong coupling, hopefully you can have an holographic description, and you can use the holographic dual of these expressions. If you are working at finite coupling constant, it may happen that you can use localization, for instance, for doing exact calculations. Okay, yes. yes, this is the normalization that you have to do to normalize with this, with the vacuum, basically. No. Well, okay, you normalize, but as usual, when you define in quantum field theory the expectation value of a of a correlated string of operators, you typically normalize the functional integral by the vacuum functional integral, which in this case is not actually the vacuum, but the dress vacuum. Okay. Okay, so basically, since this string of local operators are operators or are local operators that the defect inherits from the bulk theory, and the bulk theory, we are supposing that bulk theory is conformal field theory, you can classify this correlation function in terms of unitary irreducible representations of the superconformal algebra on the defect. So it depends how is your defect, how many symmetries your defect is preserving. And of course, classifying the whole set of one-dimensional defect conformal field theories is equivalent to classifying all the unitary irreducible representations of all local operators that you can define on defect. There are a lot of conformal data that you can compute, which will uniquely define your theory. One-point functions, this is something new. Of course, since the vacuum is dressed, in this case, the one-point function is no longer zero, because when I talk about the one-point function, I mean this object, and this is actually a two-point function, so it's no longer zero. We can compute anomalous dimensions computing the dressed two-point functions. We can compute the OPE coefficients computing the three-point functions, and so on and so forth. And you can apply also in the defect case many well-known techniques like bootstrap, localization, integrability, or, as I said, an holographic description. Moreover, we do have a new bunch of conformal data, because now we do have also non-trivial correlation functions between operators defined in the bulk and operators localized on the defect. So we have these bulk boundary correlators, and this is an extra set of OPE data that we can use to characterize our theory. Okay, and so hopefully we can even infer properties of the bulk theory from what we know on the defect. Okay, so this is basically a set of motivations and general scheme. So in this framework, my primary interest now in this seminar will be to give a little contribution to the general problem, one of the central problems in theoretical physics, which is the identification of the space of theories, what we call the theory space. So we will attempt in a particular set of operators belonging to this BJM theory, we will attempt a classification of one-dimensional defect conformal field theories, basically classifying fixed points of RG flows and describing the RG flows that connect different fixed points. My setup will be Chern-Simons matter theories, in particular ABJM theory. I will review for you the main features of this theory. And the plan of the talk from now on will be the following. So first of all, I will review the classification of all BPS operators in ABJM. Then I will show you how we can study RG flows and why there are RG flows, and how can we use them to connect different fixed points. I will provide a defect field theory interpretation of our findings. In particular, I will focus on the irreversibility of these RG flows, which goes under the name of G theorem. I hope I have time enough to talk about cohomological anomaly and framing, which is sort of caveat in all this construction, and then I will conclude with some comments about future work. Okay, for the time being, this is it, because now I move to the blackboard. So, as I was mentioning already, this is what you might have in mind when you think of a Wilson loop in gauge theory. However, thank you very much. What we can do is try, and this has been done, of course. Maybe I should give you a few information about BJM, or you are familiar with it? Shall I just briefly? The only thing that we have to take in mind is the field content. Where do I find the eraser? Okay, I'm going on. Thank you very much. Okay, so let me remind you here that ABJM which stands for Aroni, Berman, Jafferi, Maldacena. That is the theory that was proposed in 2008 as the dual of, as one of the two main characters of the three-dimensional version of ADS-CFT correspondence. This is a quiver theory associated to two gauge groups. Typically, these are U1 and let me call it U hat N. So associated with these two gauge groups, you have two gauge fields, A and then A hat. And on top of everything, you cook your theory by adding matter. And matter is a set of scalars, 4 scalars. I goes from 1, 2, 3, 4. It is an SU4 asymmetry index. Okay, and you have C. You have these are complex scalars, so you have the complex conjugate C bar. And together with C, since we want to build up a supersymmetric theory, you will have the corresponding fermion both here and here. Okay. These are in the bi-fundamental of the gauge groups, and these are in the bi-anti-fundamental of the gauge groups. You can write down an action, which is a highly interacting action, because you will have, of course, the gauge part, which is Chern-Simons action for A minus, indeed, Chern-Simons action for A hat. Then you have the usual kinetic terms for the scalars and the fermions. But the most important thing is that you have a highly interacting part of this action, which contains in components a pure scalar potential, which is contains 6 scalars, and sort of Yukawa coupling between scalars and fermions. Okay, if you fix, so the Chern-Simons are featured by level K and level minus K. If you fix the coefficients of this interaction part suitably as a function of K, you will end up with a theory which has n equal to 6 supersymmetry. This is the most important thing. Yes?
When you write the kinetic term, is the gauge invariant? So like
sorry, this is the kinetic plus no minimal coupling. Okay. So, sorry, minimal coupling. So it is written in terms of covariant gauge, covariant derivative. Yes, yes. Okay, so you have a non-trivial coupling between matter and the gauge sector, but the matter is interacting.
Is it important?
No, 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 in fact, there is an obvious generalization. In fact, what I'm going to tell you holds for most general case. You can even have N1 and N2. From a field theory point of view, nothing changes. Basically, from the holographic interpretation, of course, there is a little bit of changes. But yes, I'm concerned that we can consider even N1 and N2. Easier if you set N1 and equal to N2, but okay. Because in this case, you have, so the coupling constant, for instance, the coupling constant for the ABJM case is N over K. If you move to the ABJ, this is what is people call ABJ theory, you have two coupling constants, 1 and 2, and of course you have to deal with two coupling constants.
Was it ever done for different groups? Can I put exceptional groups in there?
Yes, people have done some generalization to, honestly, I don't remember which kind of, yeah, but you can do, for sure, some generalization. Yes. OSP, yes, yeah, probably. OSP, yes, probably something like that. Okay, what is important? Okay, probably it's not necessary, but you should know that this theory describes the low energy dynamics of a stack of M2 brains, and it can be holographically described in terms of M theory on ADS equal to, yeah, M theory on ADS4 cross S7 over ZK, so we have an orbifold in this case. In fact, we do not have maximal supersymmetry. Or when you take K, I don't remember, it is K, yes, K power 5 much bigger than N. Let's stick to ABJM. The M theory circle shrinks to 0, and you are back to a dual description in terms of a string theory, type 2A, string theory on ADS 4 times CP3. Okay, so what is very important to remind you is that this theory is finite. So it sits at its superconformal fixed point. Okay, it means that the coupling constant does not run. And that implies that you can study the theory in the 3 different regimes, as I was already mentioning. When lambda is small, we can use perturbation theory. When lambda is big, we use, of course, the dual description. Where lambda is finite, a lot of work has been done using localization. Okay, and you can even find, exact results with the power of lambda. Okay, so for this theory, I want to construct Wilson loops. Of course, we could start from this very famous and simple Wilson loops, but what I can do in this case, and I will tell you why, is since I have matter in my theory, I can try to generalize this holonomy, including matter, in such a way that we may gain some supersymmetry. So we are going to construct Wilson loops that preserve a fraction of supersymmetries. And this is what we call BPS, Wilson loops. Okay, why I can do it? Because, well, I would say simply because of dimensional reasons. We know that in order to construct this object, let me put it this way. This object is well defined because a mu has dimension 1, the naive dimension, classical dimension 1. In 3 dimensions, scalars have dimension 1/2. Therefore, if I consider SU4, for instance, if I consider an SU4 singlet of the form CI, C bar I, this has dimension 1, and nothing prevents me to include this term here. And I will tell you later that I have to to include it indeed. But this is not the end of the story, because in 3 dimensions, fermions have dimension 1. So I can even think of deforming this connection by adding fermionic contributions. Okay, how? So let me go step by step. Let me start.
Is it possible to get ABJM from dimensional reduction like you do for n equal 4 superior means?
From 10 dimensions, yes.
Okay.
Yeah, you get, yes, absolutely. In fact, I must say that the best way to get to this point is doing a dimensional reduction from 4. From 4, so you are left with an extra component of the original A mu, which is now a scalar, but this, I mean, it's an interactive scalar, and when you remove it from your action, you produce all the interactions. Yes. Okay, so I would say, let me see how I will include matter in the definition of my Wilson loops. Just to be definite, let me choose, and this is a choice that I will keep fixed for the rest of my talk. So I will choose C to be the maximal circle on S2, which means if this is S2, my contour will be always the equator here. Okay, this is C. Good. Which means that I can parameterize the circle with an affine parameter, let me call it tau. And this is the coordinates, the way you write the coordinates of your Wilson contour in terms of the parameter. Good. So the first thing that I can do is, let me go step by step, is to consider what I was mentioning here, adding a singlet. So what I can do is to generalize the previous expression to something like trace the path order of e to the minus I, the integral of my circle of, here I should put all my nice couplings that are minus 2 pi I over k, ci, c bar I. Okay, what is this, sir? It is something interesting. It is not BPS at all. But this is what we should identify with the ordinary Wilson loop in ABJM. So the ordinary Wilson loop in ABJM is not that one, it's this one. Why? I can give you a couple of arguments. The first argument is because, suppose that we have to find out what we define, what we mean with the ordinary Wilson loop. And mimicking what people have done in n equal to 4 superior mills, ordinary Wilson loop means the Wilson loop which preserves the maximal number of generators of the R symmetry, as in this case SU4. Okay, so in particular, I'm looking for an operator which preserves the whole SU4 R symmetry, and in fact, in this case, okay, this is neutral, so it preserves. In this case, this is a singlet, so nothing prevents you to add this term. Moreover, if you start doing quantum calculations, you start in particular using, for instance, perturbation theory, because we work for lambda small, you will immediately realize that if you do not include this term gets produced at quantum level, of course, because this has the same dimension of this one, and operator mix. So this is what we identify with ordinary. In fact, you can have what we call W plus with a minus, but we can also have a W minus which has a plus, nothing changes. Okay, but as I said, this has nothing to do with the BPS because this does not preserve any supersymmetry. Maybe to this one. Yes, exactly. Let me put in another way. The original Wilson loop is not a fixed point, whereas this turns out to be a fixed point. I will show you in the RG flow. Yeah, of course. So sorry. Whenever I talk about a W, there is the analog W hat written in terms of the other one. Altogether? No, because of the, I would say no, because of the gauge representations are different. Because this is in the adjoint of one of U1, and this is the adjoint of the other U1, UN, sorry. And still, if I have a hat here, I have to put CI bar, because they belong to different representation. You could factorize, yes, but yeah, I would say that even the expectation value eventually is just the product. Yeah. No, not really. At classical level, yes, but not maybe at one loop, yes, yet, because yes, still because you have only gauge corrections, but as soon as you get higher order corrections to matter makes everything. Yeah, it might be more complicated. Okay, now let's go to BPS. Okay, the first thing. We don't know yet, but it will be. Yes, it is at fixed point, but we don't know yet. Okay, so what I can do is, of course, generalize what I wrote there. Do you see? Yes, there is sort of shadow here. Sorry, e to the minus I e mu x dot mu minus 2 by the usual coupling that I could even put equal to 1. And now you can have a more general situation where here I insert a matrix. This is the scalar coupling matrix. And according to the particular choice of this matrix, you may improve the situation and get something which is BPS. In fact, what happens is that if we are on the circle and this matrix M is the diagonal 1, 1, minus 1, minus 1, this turns out to be 1,6 BPS. I didn't tell you that ABJM preserves 24 supercharges. So 1,6 means that this Wilson loop preserves 4 supercharges. And what is also important is that this choice is not random. It is related to the fact that in order to preserve 1/6 of the supercharges, I need to preserve an SU2 cross SU2 subgroup of the R symmetry. Okay, you can do this for A. You can do the same thing for A hat. So you will produce a W hat with the same matrix.
Gauge, regarding the gauge indices, all the terms in the argument of the integral are in the adjoint representations here?
Yes.
Okay, so you grab the way that they...
Yeah, this is something like, let me see if I can cook for you. This is fundamental, anti-fundamental, fundamental, and then, of course, when you take the trace, Okay, so this is the adjoint. This is also IJ. Okay, now let's go on. As I told you, I could even think of adding fermions because the dimensions allowed me in 3 dimensions. So what I do at this point is to consider a new expression, which is the following to begin with, e to the minus I, the integral of, and now I do construct, do you mind if I call this expression, let me call it curly A, okay? I do construct a new matrix which has curly A here, curly A hat here, okay? And as long as this is 0 and this is 0, this is an ordinary matrix, and I simply moved from what we call a one-node Wilson loop to a two-node Wilson loop, because now we include both nodes of the quiver, okay? But if I now promote this matrix to be a UNN supermatrix, it means that I can remove this 0 and replace them with something Grassmannian, let's say. And in fact, here is where we can turn on fermions. Okay, now what happens if you, now be careful, because now if you want to increase the number of preserved supersymmetries, you have to change both the scalar coupling matrix M, and you have to trigger these new couplings eta eta bar in a specific way, but I don't want to write all the expression. However, it happens that if now M is the diagonal minus 1, 1, 1, 1, and you choose appropriate eta eta bar, eventually you preserve 1/2 of the supersymmetries, which means 12. So this is what we call W1/2. And even here, you can have a plus or minus, depending whether here you put plus or minus.
All of these will be conformal in the end?
This is something that I will tell you later. However, just to, yes, to prepare for the rest of the talk, W16 is fixed point. W1/2 is fixed point, but this is not the end of the, this will be fixed points, okay, fine. But we will find other fixed points later. However, let me just stress that in order to have this operator preserving half of the supersymmetries, I need the operator preserving an SU3 inside SU4, and in fact, this is the reason why I have the change of sign in my matrix. Eta eta bar, in function of? Yes, it contains K, yes, but it is a function. I will tell you in a moment, which is the most general expression. Okay, this is the first operators, what was introduced by Drucker, Plewka, Young. And this is the famous Drucker-Trancanelli operator. But this is not the end of the story, because at this point, they, and then we went on, you can build up some sort of machine to see which is the most general expression that you can write as a function of a supermatrix in such a way that W preserves some supersymmetry. And the minimum number that we require to be preserved is 1, okay? So there is a possibility to build up an operator which eventually will be 1/24 BPS. Yes, the answer is yes, in fact. So what happens is, let me see if I can give you, let's make a sort of little table somewhere. Now I can, yeah, you don't care about ABJ M anymore. Okay, so the most general BPS operator, most general, I mean less constrained, however, BPS is, as I was mentioning, W 1/24. Let me write this way. Okay, what happens is that the structure of the operators is what I wrote there for W1/2, but now you have the M, eta, and eta bar couplings are functions of 8 complex numbers, alpha I, alpha bar I, beta I, beta I. Let me call J, beta bar J, where I and J are 1 and 2. Okay, alpha bar is not the complex conjugate of alpha, so you really have these 8 complex numbers. For generic alpha bar, beta bar, you can write down such an operator. And the main difference compared to what I was writing before is that the scalar coupling matrix is no longer diagonal. So you have also off diagonal components. Okay. Good. Then if you restrict, so this is our starting point. Now you can take this starting point and you put extra constraints on these numbers, these scalars, sorry, on these parameters. And what you find is that suppose that you fix everything equal to 0, so alpha bar, beta bar equal to 0, this will give you W16, the W16 that I wrote before. Okay, because if you set everything to 0, eta bar goes to 0, so you remove fermions, and the matrix becomes, again, the diagonal -1, -1, -1, 1. Okay, but you can even do something else, and something else is the following. You can keep beta J and beta bar J equal to 0, but now you allow for non-trivial alphas. Of course, when I talk about alpha and beta, you can think of that you could also invert the role of alpha and beta because you have SU2 symmetry. And this will give you a new set of 1/6 BPS that I will call fermionic, that were introduced by Chunbao Wu and collaborators. These are of the form of the W1/2 that I was written before, but with this precise condition, you reduce the number of supersymmetry preserved. Okay, and finally, if you set, for instance, beta J and beta bar J once again equal to 0, but now you further constrain your alpha to be equal to 1, you will produce the W1/2 plus. The minus, so W1/2 minus, is obtained by exchanging the role of alpha and beta. Okay, so basically these are the main set of BPS operators that I'm going to discuss, together with the original, what we call ordinary Wilson loop in the theory. Good. So what happens now is that we might think of W1/24. Yes. No, in the generalization, in the total generality, they are numbers. They are not integer numbers. They are complex number in general, and the matrix is not diagonal. Okay, as soon as you fix one of these sets equal to 0, you kill all the off-diagonal terms. Okay, and here in the W16 fermionic, you still have diagonal entries which depend continuously on these non-well-defined numbers, whereas when you go down to alpha phi bar equal to 1, you get the usual diagonal minus 1, 1, 1, 1. So you recover what we have already found. Now, what happens? It happens that I might think of writing, for instance, W1/24 as the W, let's say, 1/6 or W1/2 plus something else, okay? Or even more, I could think of constructing a totally generic W, which at this point is not even BPS, as the W16 or W1/2 plus something. And the suspect is that this plus something can be considered as a marginally relevant deformation of my fixed point, and so they will possibly drive an RG flow. Okay, so this is just a suspect, of course, and now let's see whether this is true. And I must say that the first investigation of RG flows between Wilson loops was introduced in n = 4 super Yamis by Polchinski-Sully, famous paper. I'm going with I should stop in 10 minutes.
No, you have 43 minutes.
Ah, okay. I was panicking. Polchinski-Sully in 2011. They were studying n = 4 super Yamis. For n = 4 super Yamis, let me tell you the story because this is much easier than ours, so probably even more comprehensible. And super Yamis. In n = 4 super Yamis, you can construct a W1/2, so 1/2 BPS operator with the same logic by adding, so we have this, by adding something like proportional to x dot u, some coupling constant, which has to be fixed in order to guarantee the preservation of supercharges. And here you have some coupling to the 6 scalars of the theory. In 4 dimensions, the scalars have dimension 1. So in this case, the scalar, say, deformation is driven by a single field, not a bilinear field. Okay. However, you can always think of putting a parameter, a not totally arbitrary parameter here, z, that plays the same role of my parameters here. And you realize that for z = 0, you are back to what in 4 dimensions you call the ordinary Wilson loop. And whereas for z = 1, you get the 1/2 BPS. Okay. What they managed to describe, indeed, was a flow, an RG flow, between the z = 0 case down to z = 1 case. And why do you have an RG flow? This is something that I will better describe in my case, because now if you use this Wilson loop and you study the one-dimensional theory defined on this Wilson loop in the presence of this parameter, you will discover that you start producing ultraviolet divergences, short distance divergences. The cancellation, the renormalization of these divergences requires a non-trivial renormalization of this z parameter. So you have a non-trivial beta function for this parameter that they computed at one loop. And this beta function has indeed 2 fixed points. One for zeta is something like z times z squared minus 1. So it is 0 for z = 0, and it is 0 for z = 1. And you can even study the flow. My arrows always go from the ultraviolet to the infrared, so the flow indeed goes in this direction, because you can realize that this deformation is going to be a marginally relevant deformation close to this ordinary Wilson loop, and this marginally relevant deformation will drive you towards an infrared stable fixed point, which is the 1/2 BPS. Okay. The same thing happens in my case. However, what is, I would say nicer in the ABJM case is that we have a big spectrum of BPS operators and non-BPS operators. So, studying the RG flows in this case is much more, of course, complicated, but even much more, let's say, rewarding, because we have a lot of more information about the theory. Okay, so this is basically what happens, what we have to do. Okay, I can give you now one. We studied a lot of possible deformation, of course. I will give you just a couple of examples in order to show you what happens. Yes, this can go away.
All of the one with one pixel point.
Let me see what I know. We will discover that W1/24 is not a fixed point. This is, in fact, true, genuine perturbation, marginally relevant perturbation. Yes, yes. Okay, so let me consider the simplest case, which is, of course, the bosonic case. Turn off all the fermions. Where is the white one? Yeah. Okay, so let me start from W minus. W minus, remember, is one of the two ordinary Wilson loops. So you have a mu dx mu plus 2 pi I over k ci c bar I. Okay, and add the perturbation. So I will call this perturbation something like 2 pi, let me put minus to stick to my conventions. Yes, 2 pi over k ci delta m I j c bar j. Okay. Of course, I can choose many different perturbations in order to stick to something doable and easy to understand. Let me take perturbations that are diagonal matrices, okay, of the form Z1, Z2, Z3, Z4, and big zero here, where these are totally generic parameters. Okay, so what we have done is the following. Now, this is your complete operator, okay? We insert this operator in the path integral, and we study the theory. Okay, we are on the circle, actually. We study the theory, the one-dimensional theory defined on my circle, and featured by this W. So when I consider, correlation functions, or even before correlation function, let me take the partition function of W, I have to compute this quantity. Okay, in computing this quantity, we applied a very smart procedure, a very smart technique that was introduced in the past for QCD. I don't want to enter these details, but when we compute this quantity, as in the n equal to 4 case, we find that there are short distance singularities that we have to regularize. First of all, we used dimensional regularization, and then we have to renormalize. Okay, since we have a non-trivial renormalization of these parameters in order to cancel these divergences, eventually we do produce and this is what we did compute, non-trivial beta functions for each of these parameters. And at the order we did the calculation, they look like this expression. Okay, it's important to observe that this beta is one loop order in the bulk coupling constant. This is the Abijay coupling constant, but it is exact in the power of my one-dimensional parameters. Okay, and now, of course, you have to ask yourself when this beta function is r equal to 0. And of course, we have the spectrum of possibility. If we set all the coupling constants to 0, we are back to our original point, W minus. But then we can even have that all the parameters are equal to 1. In this case, it means that you are correcting this identity matrix with a -2 identity matrix. So basically, you are simply changing this sign, and you flow to W plus. Okay? So you get this is W minus, you get W plus. And even more interesting, you can try, for instance, to set psi1 equals to psi2 equal to z21, let's say, and the other two equal to 0, or vice versa. And in this case, we produce the W16 bosonic. Okay. Notice that this choice preserves SU2 cross SU2. That's why we are going to W16. And finally, if I want to preserve an SU3, so I can set Z1 equal to 1 and all the rest equal to 0, or A equal to 2, 3, 4, you find new fixed points that we did not include originally in our table. And these are bosonic because I turn off all the fermions, SU3 preserving Wilson loops. Okay, and if I plot the RG flows, so I plot the behavior of beta functions, I should have here okay, this is what we find. Okay, so I use a black square for W plus W minus, the ordinaries that do not preserve any asymmetry, and the blue bullet are the 1,6 bosonic. And for instance, this is the plot when you choose psi1 equal to psi2 and psi3 equal to psi4. So you see, there is, we can easily see that, you know, your original point that was W minus, maybe I can use W minus is here. This is an ultraviolet unstable fixed point. So presumably the deformation that I'm adding is marginally relevant. And this drives me towards W plus. Instead, 1,6 seems to be something strange. In fact, we will discover that it is in this picture, it is a saddle point. So the actual flow is between W minus and W plus.
Is based on physical response?
What do you mean with physical?
Unitarity bound.
Sorry,
Unitarity bound.
Unitarity bounds. Yes, this is something that we'll discuss later. Sorry, when we go to G theorem. Yes, these are theories that did. Yeah.
To see if I'm following correctly, because many times we study this from a different point of view. It's like your deformations are inserted in the defects themselves, not in ABJM.
No.
These operators
Are localized on the circle. It's not something. The bulk is spectator. Yeah, untouched, completely untouched.
Would you expect the same kind of magnitude to exist somewhere else? I mean, in the ambient theory, in these operators, or there is a primary notation to
I don't know, because I know that if I compute the anomalous dimension of this operator in the defect theory, the anomalous dimension turns out to be negative. So the dimension of the operator in the defect theory in one dimension is 1 minus something, so it is marginally relevant, and that's why I flow. But if I compute the anomalous dimension in the bulk theory, I would not expect it to have an anomalous dimension, presumably. The theory is conformal. And this is a well-defined operator in conformal theory. No, not really. No, it is not protected. No, this would get some anomalous dimension. It's not protected. This particular one is not protected. So it might be that you can flow somewhere else. Yeah. Also in this case. There are other operators that we use to perturb that instead are protected from the bulk point of view. I need a curve, but what I'm doing now is to localize operators on the curve. Yep. What is the role of bulk? Why what bulk matters? Because when I compute the path integral, the functional integral, to evaluate this object at quantum level, let me talk about applying perturbation theory. Of course, I start producing a number of diagrams which also contain bulk interaction vertices, and therefore, you may have, let's say, contributions come from defect propagators, but also defect bulk propagators or bulk propagators. So.
Yeah, I think what I didn't understand was like the question I think was related to defining these deformations.
Yeah, because in principle, these operators, when I, where is my operator? This is an operator that in my construction is localized on the defect. It's one-dimensional defect, but in principle, this is an operator that you can define in any point of the bulk. No, but I'm just talking about the operator that you are using for the deformation.
But if you add it to the action, it wouldn't have the correct dimensions.
Which action? It doesn't, yeah, but I could think of, I don't know, adding powers of this operator, and it should be fine. Yeah.
There's a question there.
Yes. No, in this particular example, I do not have any supersymmetric point which is stable, but I will later in the other example. Yeah, the W16 seems to be not even nor stable nor neither stable nor unstable, just saddle point. Yeah. I will try to answer this question later, because this question also applies to W1/2, because even in that case I have plus and minus, and in that case it's even more serious. it seems that basically, from a construction point of view, they simply differ by a sign, but they do have deep differences in the physical behavior. In fact, when I'm going to discuss, if I have time, the G theorem, I will tell you that, for instance, while W1 plus is a unitary theory, a unitary defect theory, W1 minus turns out to be non-unitary. So G theorem is broken and nothing works. But this is simply because you change the sign in front of the coupling. Yeah, so it seems to be. I will say something at the end. Okay. If you want just a brief answer now, you can have an holographic description of RG flows. Presumably not in this specific case, because I do not have an holographic, I mean, I should have, but we do not the holographic dual of W plus W minus. When you consider, for instance, flows between W16 and W1 where you do have an holographic dual, the dual of the RG flows is described by what people call the interpolating boundary conditions in the internal space, because W1 is localized in the internal space, W16 is mirrored on a CP1, okay? So you can introduce interpolating boundary conditions between total Dirichlet or Neumann plus Dirichlet that drives you from 1/6 to 1/2. But this has been proposed still by Polchinski, Stanley, for n equal to 4 superior means. In 3 dimensions, there are works, papers by Correa and collaborators, but they stick to interpolating boundary conditions that preserve conformal invariance, so they are not suitable to describing RG flows because, along the flow, you are not conformal. So this is something that should be done. But the idea is to use these interpolating boundary conditions. If I move to loops here, yes, this is something that we ask ourselves. Well, you could even do the two-loop calculation, but we do expect that you cannot modify much the behavior because two-loop correction is should be in principle much smaller than the one-loop corrections.
Is it just for one loop or can be understood from this segment?
Can be understood?
This segment is so
Sorry, I don't understand you. Can you translate? Sorry, I'm rude, but I do not understand.
Do you mean why if it can be understood non-perturbatively the structure proportional to Z? That this psi parameter.
If I have a non-perturbative corrections.
Or like a reason why non-perturbatively it will always be multiplied by Z times Z minus 1.
Of
Just one loop.
non-perturbatively, I don't know what to do. I should rely on the holographic description. This is what the holographic description is telling me. Yeah, yeah. No, yeah.
Can I just quickly, is that are any of these deformations defined? Can be understood as deformations on like displacements on the line of tilts of the
not these specific ones, no, because in fact the displacement has a different operator. Yes, yeah. So these specific deformations, no, you cannot. I would say that in that case you do not flow. You just break things. Yeah.
So previously that there is no.
No, there should be, it's just a question that one should construct them. The point is that since these operators preserve the whole SU4 symmetry, they should correspond to totally Neumann boundary conditions. So it should be completely smeared in CP3, but I don't know, nobody has done the actual construction.
If I believe it, this problem, conformal just for 0 and 1. So between 0 and 1, what symmetry do we still have?
This depends the way you deform the Wilson loop. In this specific example, you do not have any symmetry. But I will show you that you can even construct what we call the enriched flows. And these are flows that are basically built up by a sequence of non-conformal, of course, but BPS theories. Okay, in this case, you do not preserve any. Okay, maybe, I don't know if I have time to give you the second example, so maybe we should go on. The second example was about, deforming. Maybe I can simply show you the picture. Come on. The second example was simply, complicating the situation by adding also fermionic deformations. And I will give you simply this picture. Okay, now you have more dimensions in your flow, of course, because you can have four parameters. We still stick to diagonal deformations in the scalar matrix coupling. So you have 4 parameters there, but then you have a number of parameters for in particular one, we choose one, for the fermionic deformation. So you are adding an extra dimension to our flow. So what I showed you before is the green plane. When you set chi1, what is, I don't know if you can read it. Chi, the vertical line is the fermionic parameter, okay? If you set it to 0, you reproduce what I showed you before, but now, and this point is still W minus, okay? But now if I also deform with the fermionic deformation, I move out of this plane, and what is nice, at a certain point, I reach this triangle, which is, well, W1 half. The maximal supersymmetric Wilson loop. And so this is, okay, kind of nice. Okay, now, enriched flows, as I told you, I can even choose a particular deformation in such a way that, suppose that I start now from the 1/6 BPS instead of starting from W minus. In this case, adding a suitable structure for the deformation, and the deformation has to contain both scalars and fermions. I'm driven out of this point, and all these lines are now 124 BPS. So all these points along the lines are defect theories, which are not, of course, non-conformal, but they are still BPS, 124th BPS. And what is nice is that, in particular, if you move along the horizontal axis, these green arrows, this is a set of 1/6 fermionic, 1/6 BPS fermionic Wilson loops, which drive you from the 1/6 bosonic to the 1/2 BPS. So we have, in particular, this nice enriched flow, which connects W1/6 and W1/2, for which we could have an holographic description, in fact, because we know the holographic description of 1/2 and 1/6, so we might try the holographic description of the RG flow. Yes.
The previous slide where you showed this dimension,
Mm-hmm.
you have these blocks that stayed on one plane. Probably the one
Yes, the first example.
that some of the other operators will just turn on at 2 loops, and I will eventually always go to the red 1/2 flaps that you have.
No, I don't think so.
They are not protected.
Yes, they do not, no, not really protected, but they do not mix with these deformations.
So is there any 1/6
Fermionic.
conformal?
Not conformal, because they are not conformal. Sorry, not this one. They are not conformal because, of course, you are flowing.
Okay.
but they are 1/6 fermionic.
Yes, but there is no 1/6 fermionic
Conformal, no. You have to go to bosonic. Yeah. 1/3. 1/3 exists, but it's much more complicated. I think Nadav introduced it. It's a product of Wilson loops. This is a possible development of this investigation, considering, flowing between more complicated structures. Yeah.
No, still do not know the object structure.
Yeah, this is basically what we have. Yeah, the most general construction. This is.
The most general is mean still do not know how to do the one third, but this is about your
Could you get one of
No, they understand the question. No, but you should take into account that when I say most general, it's more general within my initial framework. It is not the most general, because you remember that, for instance, I decided to stick to deformations which has diagonal scalar matrix coupling, scalar coupling matrix. It might be that if you deform with something which is no longer diagonal, you flow somewhere else. But the point is that we have a lot of runaway directions. So I don't know if sooner or later you reach something interesting. Yeah. Okay, so this is basically the summary of what we found. And now we may move. How much? 10 minutes? No. 13. Fantastic. I can reach the point where I mentioned framing for you. Okay, so this is basically a summary. So the flows are indicated with the lines. The green lines, they are the enriched flows, and you see that we have all the basically the BPS and non-BPS Wilson loops that I have described so far. Okay, and now we want to try an interpretation of these flows from the point of view of the defect theory. Maybe, let's see if I can keep that turned on, but it will turn off anyway. Okay, forget about it. Okay, so what we can do, first of all, at the fixed points, what I was already telling you at the beginning, at the fixed point, we have defect conformal field theories. Actually, they may be super conformal field theories, one-dimensional super conformal field theories. And in fact, for instance, let's consider W16 bosonic. In this case, this is a defect super conformal field theory with supergroup SU111. If you have W1/2, same thing, but in this case, you have more supersymmetries. So this is the one-dimensional superconformal group in this case. What you can do at this point, one thing that we can do, which is just to complete our understanding, although I would say it's already quite under control, is to compute the anomalous dimensions of the perturbations that I added, okay? How do I compute the anomalous dimensions? Okay, there is a very easy way to do it, which starts from the simple statement that as long as you are at the fixed point, you cannot, your defect field theory cannot have any stress energy tensor. Why? Because in one dimension, the stress energy tensor has a single component, and the single component has to coincide with the trace, but the trace has to be 0 because we are at the fixed point, okay? So at the fixed point, the defect stress tensor is always equal to 0. However, when you turn on a deformation, perturbation, you will gain, so you get out of the fixed point, so you will gain a non-trivial trace, so a non-trivial defect stress energy tensor, which is, of course, proportional to the beta function times the operator that you are using to deform your theory. Okay? There is a very straight condition on this stress tensor. The dimension of stress tensor has to be equal to 1, protected. Okay, so if you use this this condition, basically from a little algebraic calculation, you will find that if we define the quantum dimension of an operator in this way, suppose that we also have mixing. This is minus delta ij plus d plus ij. Okay, this is the anomalous dimension, the quantum dimension. You will find that the gamma ij is nothing but the derivative of the beta function of the of the I deformation parameter respect to the j parameter. Okay. But so these are all the parameters that enter the perturbation. At the order that we were working, that there is no mixing, so this is going to be a diagonal anomalous dimension matrix, and from the explicit expression of our beta functions, we can compute the anomalous dimensions. And what we found, of course, this is just a consistency check, well, even without picture. Remember all my flows. What we found is that, of course, around, for instance, W minus, where you have all these flows going away, the anomalous dimension of the perturbation is negative, and in fact, the operator has a total dimension 1 minus something, so it is what we call the marginally relevant operator. Except for the W16 bosonic, that's why I was telling you that it is a saddle point, because in that case, for the W16 bosonic, remember that I have to set the 4 parameters equal in pair. And in this case, we do find that because of the structure of the beta functions, this is the operator which this corresponds to C1, C bar 1, to C2, C bar 2, and so on and so forth. We find that Y C1, C bar 1, C2, C bar 2 has anomalous dimension negative, so this become marginally relevant. The other two, C3, C bar 3, and C4, C bar 4, they get anomalous dimension positive. So in those directions, you flow in the opposite direction. That's why W16 bosonic is not a good ultraviolet or infrared fixed point.
Next question.
Yeah.
If I consider a protected, so something that has gamma equal to 0, does it mean that when I deform, I can...
You do not flow.
I don't flow, so
No.
I get
Yes, because if it is protected, this is why, for instance, I cannot use scalars in protect multiplets of the ABJM, because in that case, you don't flow.
You stay in a...
Yeah, because in that case, your deformation is exactly marginal, so you stick there. Okay. Good. Another thing where now I have no time to spend many words, but it is very, very interesting, important, is what I was mentioning at the beginning, the G theorem, that has been studied long time ago for two-dimensional theories, for one-dimensional theories, has been developed recently by Cuomo, Komargowski, and Rashid Mose for generic one-dimensional defects in a generic d-dimensional conformal field theory. And what they found is that thanks to a very smart identity if you consider that, you know, if you take a log of my partition function, this is what I would call the free energy of my theory, okay? And I can compute this quantity at the in my flow at the ultraviolet fixed point. Let me call it this G ultraviolet. I can compute the same quantity at the infrared fixed point. Let me call it G infrared. And what they proved is that if you have a flow between an ultraviolet and an infrared fixed point for a defect field theory, which is, okay, in Minkowski should be unitary, in Euclidean should be reflection positive, you always have that G ultraviolet is greater than G infrared, as expected in any ordinary theory where ultraviolet and infrared has a meaning. But in fact, in terms of their, I mean, basically the main identity that they used to prove that this theorem is an identity which contains the two-point function of the stress tensor, the deformed stress tensor, TD. And the condition is that this two-point function has to be positive, which means that the theory has to be reflection positive. Okay, fine. So we did apply, basically, we did compute this quantity in these quantities in all our flows, and we did find that all our fixed points respect the G theorem. That means that all our fixed points correspond to unitary reflection positive defect conformal field theories, except, as I was mentioning before, the flow that concerns W1/2 minus. This flows towards W minus, I think. No, sorry, WSU3. Along this flow, we have a swapping sign, and what we do get here is this condition. So G theorem in this case is broken, which basically is telling me that this theory is no longer unitary. So this is the only case of non-unitary theory that we found. How much time do I have now? 2 minutes, framing. Okay, so there is a caveat in all this construction, which is the following. Let's take the flows which involve BPS Wilson loop. Let's stick to the enriched flows. Remember, for instance, I can flow from W16 to W1/2 through a list, you know, a bunch of W fermionic 1/6. Okay. So since you have a flow, what I'm telling you is that if I compute the expectation value of this operator, I do compute the expectation value of this operator, I do compute the expectation value of the interpolating operators, what do you expect? You do expect that in my calculation, they are all different because I'm flowing from one point to another, okay? However, at classical level, you can always, let me be very general, you can always, how do I say, let me just take any of them. You can always prove that this operator or this operator are homologically equivalent to the 124, which means that they can, I mean, basically the two operators differ by Q of something, where Q is a charge preserved by the two operators, okay? So, of course, Q squared is equal to 0. This is what people call the homological equivalence between Wilson loops. Okay, so what you would conclude? You would conclude that if I now compute the expectation value, I should find the same expectation value for every single operator. operator. So I should never flow. All these operators should have the same expectation value. However, in our perturbative calculations, we found that they are different because these expectation values are functions of the parameters that I had to flow away. Okay, so what's going on? The answer is framing. Okay. First of all, before telling you what framing is and why framing is the answer, let me tell you that basically what I have to conclude, if I believe in my calculations, is that my calculation is telling me that at quantum level I have a SUSY anomaly. So this Q at quantum level no longer kills the vacuum, so I have a Q anomaly, okay? And this is why we talk about cohomological anomaly. Okay. How do I understand? Well, before talking about framing, I don't know if I reached to the point where we can talk about framing if you wish later, because I prefer now to give you a vague idea, intuitive idea of what's going on and why we do. I would say we should have expected the appearance of a Q anomaly, and the reason is the following. We know that. In perturbation theory, even at a fixed point, whenever we find ultraviolet divergences, as in our case, we have to regularize the theory. And as soon as you regularize the theory, you break conformal invariance. So at quantum level, for sure, you will produce a trace of your stress tensor, which will be order epsilon if I use dimensional regularization. Of course, at the level of word identities, who cares? When I send epsilon to 0 at the end of the calculation, I'm back to the conformal point. However, these order epsilon terms may enter quantum calculations, and if these order epsilon terms are multiplied by 1 over epsilon divergences that come out when I replace bare quantities with renormalized quantities, they can give rise to finite terms. Okay, so that's why I may have some finite contribution from here. Since I am supersymmetric, I am a supersymmetric woman. If I have a trace anomaly, this trace anomaly has to belong to a SUSY multiplet. And it is well known that inside a SUSY multiplet, there is a Q anomaly, a SUSY anomaly. Okay, so the multiplet, which contains the trace anomaly, contains also what people call the gamma trace anomaly for supersymmetric charges, because this is no longer 0, whereas it should be 0 to have everything under control at quantum level. Okay. In addition, because of this contribution, this will be still order epsilon, of course. In addition, as a consequence of this, of the appearance of this multiplet, we do also have that the spatial superconformal transformations are no longer conserved. So we break spatial conformal, superconformal transformations. Okay, in such a picture, it's obvious, once again, that if I have order epsilon terms here, when I multiply them by 1 over epsilon, I might break, I might produce finite terms that break cohomological anomaly. So eventually, I don't find anything wrong in expecting a Q anomaly, because this is sort of daughter of the fact that I was breaking conformal anomaly by doing my regularization and renormalization. There is another very nice observation that is the following, but probably this drives me too late. That is, this anomaly is related to, I don't know if you're familiar with n equal to 4 super Mills, Drucker and Gross. They pointed out that there is a conformal anomaly that makes you breaking conformal anomalies when you map the line to the circle. So why for the line all the Wilson loops should be trivial? This is on the line. When you go to the circle, we know very well that this is no longer 1. This is a function of the coupling constant. Okay, and they identify this anomaly as due to the fact that this mapping is not preserved by this mapping does not preserve inversions. Once again, since I'm a SUSY anomaly, I'm a SUSY person, I'm not an anomaly. This should have a supersymmetric counterpart. So the Q anomaly, which we are facing now, should be related to this anomaly. In fact, if we go back and compute our expectation values on the line rather than on the circle, we do find that they are all equal. They are all equal to 1, and there is no Q anomaly. So this is, I think, the closure of the story. Framing, where does it appear? If I compute, remember that I'm computing these quantities using ordinary perturbation theory. If you use matrix model instead, people claim that the matrix model gives you the same result for all the Wilson loops that are related by Q transformations. Why? Because people believe that the matrix model computes the expectation values at framing 1 without entering any detail. Framing basically is sort of change of frame that produces for you a very nice phase in front of the expectation value, which cancels exactly the Q anomaly contribution. So if I move my calculation from framing 0 to framing 1, I am safe because I am in a scheme where the Q anomaly disappears because it is compensated by framing. And this is the reason why matrix model should compute the expectation values at framing 1. That was just belief, which was based on very strong arguments, but we did compute all these quantities at framing 1 perturbatively, and in fact we found that they are all equal when we do the calculation at framing 1. So this proves that once forever that it is true that the matrix model computes these expectation values at non-trivial framing. What is framing next time? I'm done with my time. Any others? Yeah. The problem is that when you deform the contour and you get out from the circle, okay, if you get out from the circle, from the maximal circle in a very controlled way, for instance, when you go to a latitude, okay, that works. Yeah, on S2. If you start deforming in a random way your contour, I would say that generically you break any BPS. So you can still have probably some flow, but not at BPS points. You break supersymmetry completely. Yeah, absolutely. Yeah. But this has, in any case, this has to do with framing. Because if I start considering contours which are no longer planar contours, I do produce extra contributions because the normal bundle now is non-trivial, blah blah blah, and you will for sure your results will be modified by framing effects. But which is fine. I mean, we know how to control them. However, that will be for sure a generalization.
If I deform the circle, I wouldn't get it. Not only you will break supersymmetry, probably.
For sure, I break supersymmetry.
But also maybe conformal, or can you have a conformal defect?
You could have a conformal, well, for instance, W minus that I was mentioning. is a conformal point with no supersymmetry.
Yeah, but only if it's a circle, right?
Yes, but even I don't know. I should try. I never tried, but I might expect that there might be still some special contours which are not the circle, where you can still have conformal, or maybe not. Probably, yeah, probably not, because you break all the three generators of this of the conformal group. Yeah, probably.
When you compute the planar thing, the line defect that is just a train, you get all the same results. Can I think it as this deformation being exactly marginal in that case, or?
No, that was something that puzzled us a lot. Our conclusion is the following: that what happens is that they all have the same vacuum expectation value, the same, let's say, the same free energy, the same partition function, but they do correspond to different theories because they have a different set of symmetries. In particular, if you think of R symmetry, the different points corresponds to different subset of R symmetry. So we believe that they are still different defects that accidentally have the same partition function, the same value for the partition function.
That is possible if your deformation is exactly marginal.
No, it's not exactly marginal, because I'm really moving. I mean, even if I'm doing, okay, let's put it this way. If I do compute these expectation values at different framing, I'm going to modify the value of the expectation values in such a way that they are all equal. But for the beta functions do not get any correction proportional to framing. And this has a very obvious explanation, because framing is a global effect. The beta function just look at the local effects, okay? So the beta functions are different from 0 whenever you are out of the fixed point. So you still have a flow. The only thing is that the expectation values are the same. And in fact, you flow from a theory which has, I don't know, SU4 R symmetry to a theory which has SU2 cross SU2. So they are different defects indeed. No, the anomalous dimensions are independent of framing. Yes, because you can guess them from the beta functions. As I said, the beta function features your theory locally at short distances, whereas framing is a global effect. Framing eventually, okay, let me just tell you what is framing. In a sentence, if you start with your circle, the original circle, you can think of regularizing the calculation of your Wilson loop, putting some of the operators lying on this circle and the other ones on another circle, which is intertwined with the first one. And framing basically is the winding number between the two. So it is a global feature, which does not affect beta functions, of course.
So the question about this bond, whether it's physical or does it satisfy unitary bound?
Unitary bound, I don't know, but it is what I know is that the theory is unitary, because I respect the G theorem. We didn't make how to say detailed investigation of all the. We should take a one particular fixed point and investigate. Yeah, no, I know. We should construct the whole spectrum. Yeah, that we didn't do. I think so. Thank you.